Hello everyone, this is the second video regarding the finite element analysis and design of the piezoelectric based ultrasonic cleaners. In the previous video I've explained what is ultrasonic cleaning and what type of ultrasonic cleaners are used in the industry. Now I'm going to start modeling the ultrasonic cleaner. I'm going to use Abaqus 6.14. Without wasting time, I'm starting modeling the front drive of the ultrasonic transducer. I'm going to use 3D modeling and deformable solid, and I will create it with revolution, approximate size 0.4. Okay, then I'm going to use the create lines. I define different points. Starting point is the origin, then 0.035 and 0, then 0.0225 and 0.07, then 0.007 and 0.07, 0.007 and 0.05, 0 and 0.05, 0 and 0. Okay, now I have to revolve it around the axis shown, 360 degrees. So the front drive is created here. I create some partitions for better meshing the object. So in order to make a good mesh, I have to define some sort of partitions first. So this is the whole cell. I create cutting plane with point and normal. So this is the point that I'm going to use, and this is the normal, and I create a partition. Then I create another partition by define cutting plane. The whole cell is selected, done. Then this time I'm going to use 3-point partition, 1, 2, and 3. I create a partition. Now if I go to the mesh, you see there are two colors. The green color is for the structural mesh, and the other one, the red one, is for the show you here. The red one is for the sweep mesh. Usually use medial axis for better meshing. That's what I use. So the global size that I'm going to use for meshing is like 25 or 24. 0.0024, which means that 2.4 millimeters. The whole sizes that I'm going to use is based on metric systems like meter, Newton, whatever. And I also need to define a seed edge for the bottom edge here, done. And then I bias double and I flip it, and the number that I'm going to use is 25 and something like 2. Apply it and OK. And then I can check the mesh. I'm going to use the linear shape functions and also 3D stress type of elements without reduced integration, and I mesh the part. It's almost a good mesh, but we have to check it. We verify the mesh here and highlight the warning and errors. There is no warning and error, as you see here. There's no warning and there's no error. Nothing is highlighted. Okay, so we can go to the part and create the second part. The second one is the back drive. I created with extrusion. create the circle 0 and 0, 0.007 and 0, 0 and 0, 0.0225 and 0. Then the sketch is finished. 0.035 is the thickness. Again, I create a partition, the cell, by defining the plane with 3 points and separate into 2 halves. Again, get back to mesh. The size that I'm going to use is 0.0025, and again I'm going to use the linear element without radius integration, 3D stress, and I mesh the whole structure. Then we go to the third part, which is piezoelectric disc. Again, I created with the extrusion, the same 0 and 0 and 0.0085 and 0, 0 and 0 and 0.0225 and 0. Done. And the thickness is going to be 0.006, which is 6 millimeter thick. Create a partition. Again, define cutting plane, 3 points. And go to the mesh. This time you have to make sure that the elements that you're going to use is supposed to be piezoelectric elements, not the 3D stress. So you find the piezoelectric family, and again linear. Every other thing is good. Okay, you mesh it and go to the next part, which is the electrodes. Again, extrusion, the same type, 0 and 0 and 0.0085 and 0, 0 and 0, 0.0225 and 0. Then 0.0006, which is 0.6 millimeter thick, very thin. Again, we create a partition here and 3 points partition, 1, 2, 3. We go to the next part, which is the meshing. Again, this is the linear 3D stress element, and the size that we're going to use is 0.0025, and we mesh it. The final part is going to be the bolt. For the bolt, I'm going to do the revolution this time. Solid element. I use the create lines, the first point 0 and 0, and then 0.012 and 0, and 0.012 and 0.01, and then 0.018 and 0.012, I mean 0.01, 0.018, 0.012, 0.007, 0.012, 0.007 and 0.0758, and 0 and 0.0758, and the origin. I revolve it 360 degrees. Then I can create partitions for this one. Define cutting plane. I start with the, it's better to start with the extrusion. Okay, so this is the edge that I'm going to use, and then extrude along direction, and this direction, and this direction is good. Okay, create partition. You see, causes this one, right? And then again, we're going to use it. These partitions are again for better meshing. Create this edge. Okay, extrude along this line. Okay, and this is going to be another partition, and then I have to define cutting plane. The whole cells are going to be selected, then point and normal, and that's the point and that's the normal that I'm going to use. Again, partition, this is the 3 points, 1, 2, and for example one of these points 3. Okay, now I am going to check the mesh parts. Yes, just make sure that this part, okay, before that I need to create 2 datums. Offset it from the top point here by minus 0.015 in the y direction. Okay, and then offset it from this bottom one by 0.035 for the x direction. The reason that I create these 2 datum points is that I want to create 2 partitions to have two surfaces which are in contact with front drive and back drive. So here I define cutting plane. This cell is going to be selected, point and normal. Point is going to be the datum point, and then the normal is here. The same procedure is going to be used, and point normal. This is the point normal. Okay, and then make sure that this part is going to be meshed based on sweep and medial axis. The size that I'm going to use is 0.0025, and the elements will be linear 3D stress without radius integration. Then we mesh it and we check the mesh. It seems very good. Before that, I'm going to make sure that this part has been meshed based on medial axis, which is, yes, correct. Okay, we are done with this part. In the next video I'm going to show you how to continue this model.